Okay, so we'll get started. Uh, as you know, this Thursday is our second midterm. As promised, it's going to cover only chapter 5 and 6. That's MOSFET and BJTs. So whatever covered in the exam is not going to be more than what we covered in class. So if you really attended the lectures or review the lectures, did your homework, you should be able to get 100% out of the exam. Just because you also have a second chance to do each of the problem similarly to before. But remember, it's the average of what you get from the two passes. Okay. I'll send a reminder as well for those who are not here today. Okay, so today we're going to conclude chapter 6, and we might get started a little bit on chapter 7. We'll see how it goes. But I'll probably go back just to go quickly over these two chapters of the contents that we have covered so far to see if you guys have any particular problems. So last lecture, we stopped at this problem. And so what happened was we have two transistors, the NPN at the top and the PNP at the bottom. And then we get a 5 volts power through a 10K resistance at the base of these two transistors. And we also got a load resistance at 1 kilo ohm in the middle of these two transistors. This is a very typical like class A amplifier that you guys might actually see in the next class. What we started looking at this problem saying, well, these two transistors can not possibly to be in the conducting mode together, or it cannot be in off mode together. But when we did some assumption to start with, we got like both assumptions right. And I ask you guys to think about what happened, why, where did we make those mistakes, right? So did you guys actually look at this at all? No? Okay. Well, I guess you guys are busy with some other classes. Okay. Well, we'll look at together then. Well, first of all, look at what we did. Initially, we said we're going to assume Q1 is on. So we assume Q1 is on because battery is infinity by given nature. Then we'll have, okay, so Q1 is on. You have Q1 VBE1 is going to be 0.7. So therefore, you have VO at 4.3, right? So VO is 4.3. So VO is 4.3, and so VO basically is VE2 is 4.3, and so somehow saying because there's no current in the base, so we said, well, this voltage over here, VB2 is 5 volts. So here at the Q2, so Q2 is off. Everything seems to be logic, right? Everything seems to be logic. Okay, so now we said, well, let's try another way to see if we actually make a mistake here somewhere. So we assume Q2 is on. So we assume Q2 is on. So VEB2 is going to be 0.7. So therefore, what is VO? So it's going to be 5 plus 0.7 is going to be 5.7. So if that's 5.7, and then that input is 5 volts at Q1, so which means the base is less than the output, the base is less than the emitter, so Q1 is off. That seems to be also right. But it can be both, right? One of them has to be wrong. So we're saying why? Why would this happen? Why we make a mistake like that? So let's go ahead, redraw the circuit. We're going to do it again. We're going to see what happened exactly with, especially we want to start with say Q2. we're gonna assume Q1 is on, and we're gonna I think let me see what I did here. Ideally, I can tell you the solution that Q2 is actually off, but we're going to start to do this problem in two parts. We're going to start with, because Q1 is on top, it's natural. A lot of people would start by assuming Q1 is on and see what happens. So we're going to assume Q1 and we're going to solve the problem. Then we're going to also assume Q2 on and we'll solve the problem again. We'll see where we made the mistake. Assume Q1 is on. And if we assume Q1 is on, so we have B1 equal to 0.7. Since VB is 5 volts, right? So this is VB 3O. So VB is 5, right? And VB is 0.7, so we got VO is going to be 5 minus 0.7. So VO is 4.3 volts. What we're going to do is, instead of just looking at the voltage, we're going to look at the current as well. So I'm going to look at the current. So IO is going to be VO over the 1K resistance. That's going to give you 4.3 milliamps. Correct? You guys follow me? Okay. Yeah.
To get that BO to be this 0.7, we're assuming that there is no current from the bodies. We're assuming beta is infinite.
Yeah, we assume beta is infinity. That was given in the problem. So we can write down here. So beta is infinity. IB is equal to 0. Okay. I would say approximately 0. We'll never say it's actually 0. So IO is 4.3 milliamps. So we got that one. And then we're going to have VB2, which is same thing. So VB2 is going to be also 5 volts. So less than, what happened? So VB2 is let's stop writing.
Please use the one bottom left.
No, I'm using this one. Yeah, I'm using this one. Should be this one. The other one, this one is for, this one actually doesn't work. That one doesn't work. No. Let me quit. Sorry. So what happened? Actually, it's that.
Oh, it's frozen.
Frozen, yeah. Let's stop sharing. Oops. Control. Let's kill the Microsoft. It's not responding.
Kill Edge.
Huh? And task, right?
Yeah.
Okay. Okay, it works again. But that little thing, actually, hold on. Let me do one more thing. Group sharing. Okay, so looks like we got it back. Okay, so we're gonna rewrite all these things that we just wrote before. So we're gonna say assume, is this too thin? Let me, huh, I can change it, the pen size. You guys, I mean, what the pen is okay? Okay, it's fine, okay. So assume Q1 is, let me erase. Okay, so assume Q1 is on. We got, also we assume beta is infinity and IB 0. That's what we assume. And then we have Q1, VBE1 equal to 0.7. And then we have VB1 equal to 5 volts, right? So therefore we have VO equal to VB minus VB U1 equal to 4.3 volts. And then IO, we found it to be VO over RO. That gives you 4.3 milliamps. So let's call this IO. This is a VB1, VB2, and so VB1 from here, sorry, from here to here. So then we have VB, also we have VB2 also equal to 5 volts because there's no current. But VO is, this is larger than VE2, which is equal to VO equal to 4.3 volts. So Q2 is off. So everything in this process seems to be logic, and all the current that goes through and it goes this way. So the 4.3 milliamp current, it goes from Q1, it goes from 5 volts to Q1, and it goes to the emitter of Q1, and then goes to 1K resistance and goes down to ground. So this seems to be good. Now last week we also got the another assumption is that if we assume Q2 is on, and then we seem to get a correct solution, but there was a glitch somewhere that we didn't catch. So that's why we need to go back saying, okay, what happened? So if we assume Q2 is on, so let me redraw the circuit. So if if Q2 is on, we would get VEB2. So VEB2 now will become 0.7 volts, right? Because Q2 is a PNP. So if VEB2 is 0.7, this Q2 is on, and VB is 5 volts. So what will be VO then? VO will be 5.7 volts. So if VO is 5.7 volts, which is larger than VB1, VB is 5 volts, so Q1 is off. Okay. So now this, so far it still seems okay. But if we continue, we want to find IO is going to be VO over the 1K resistance. That gives you 5.7 milliamps. Right? So at this time, I wish that you can see the problem. Where would you get that 5.7 milliamp current coming from?
Has to be coming from voltage, from our negative voltage. Because there is no coming from B, there is no coming from our positive voltage.
Because Q1 is off. Remember, we assume Q1 is off. But Q2, we said Q2 is on, but when Q2 is on, the current is supposed to be going this way. How can you have a 5.3 milliamp current going through that resistance without, there's nowhere the current would come from? It doesn't come from the base current is 0. So apparently, this is deadly wrong because this is not possible.
So if that was a negative current, then we'd be okay?
Yeah.
Okay.
Yeah, of course, if that, I mean, if that is something like minus, well, yeah, so if this is minus current going up, it will be fine going this way, right? So, but apparently it's not. It's a positive, so that's impossible. So that's where you will find the problem. So sometimes it can be interesting is that you started to think, yeah, it seems to be fine, but then until you get, but okay, so if there's no load resistance, that will be a different story. This circuit will be in trouble. Yeah.
So, Professor, you mentioned that when our emitter voltage is greater than our base voltage, that means it's
The PNP.
it's off, right?
No, well, for NPN.
For NPN.
Yeah. Yes.
So
Well,
for PNP, it's
It's the emitter is higher than the base.
right, and then
Yeah.
for
For-
that's for PNP,
But for PNP, yeah.
and then what? And for NPN.
For NPN, if emitter is higher than base, then it will be off.
So for both of
Yeah.
them, it's
No,
What was it for the other one?
no. So
Explain the two. I'm sorry.
yeah. So okay. So for your question is,
Yeah.
so for NPN, so VB much larger than VE to be on. But for
Must be. Got it.
for PNP, I mean not just large, but 0.7. You know, VB. But for PNP is VEB is 0.7, which means VE always larger than VB to be on, right? Yeah.
Yeah. So whenever if we find it the other way, then we know it has to be off, right?
Yeah, yeah.
Okay. Thank you.
Okay. So this is one problem, and sometimes it can be tricky. You often find many of these similar problem. This is tricky when you go to the power amplifiers, which is going to be even more interesting because you're going to have to set those devices to be either one on off or the other off, or sometimes they can be both on or can be both off, depending on the operating conditions. Like in this case, we apparently have this bottom like off. That's the final solution. But at this point, do you guys think if what kind of change if we make so that we can make this circuit opposite? We can make it like Q1 off, Q2 on. What can you do?
Mask it really nicely.
You can change VB instead. Now VB is 5. Now you can change VB to a different value, right? So now, of course, the other thing that, okay, I want to see, there's one more thing is that when you get into the real problem to solve this problem, now remember what I made it also, though actually you guys didn't catch this. There are a couple of mistakes actually we made it here. So let's use this pointer. So if you guys see here, do I have a pointer? You guys see? Okay. So I said VBE. So I said VB is 5 volts. And I said VB is 0.7. So that VO is 4.3. So if VO is 4.3 and VC is 5, so the voltage drop between 5 and 4.3 is 0.7, right? So which means this one is actually in the active region. More than 0.4.
So we want it to be effective?
Yeah, we want. Yeah, I mean, it doesn't matter. So eventually, it depending on what type of circuit you're designing. Like if it's an amplifier, it's a power amplifier. Yes, we want it to be in the active region. So that is okay. Now, if actually you if VB if battery is not infinity, if battery is 100, then we would have to actually solve for the exact value for each current, and then we need to find the actual like voltage at each node and at each current, and it won't be too much off because again, you know, this VB is very small, almost negligible, but still there's going to be some difference. So this is the final solution. One consider battery is not infinity. Well, this is what you get. Like instead of 4 point something, like instead of 5 volts, now it goes to 4.6 volts, right? So initially we assume VB is 5 volts, but it's actually 4.6, and the output is 3.9 because we use 4.6 minus 0.7. We got 3.9 instead of 4.3. So everything changes a little bit, but still the on-off status won't change for Q1, Q2. Okay.
What would be like the threshold you said when we bring our base down to a certain threshold that we switch so that Q1, Q2 turns on? What would be that?
Oh, you mean for what VB? Well, we have to calculate it. I mean, apparently, if you bring that VB to minus 5 volts, you definitely would switch that too. So if it is in the middle, I mean, you can do. Yeah, if it's the middle, I would say, you know, it is possible that both will be off instead. So that's where when you get to class A amplifier, you have this called distortion between +0 and -0. There's no output. The output is 0 because if it's 0, what happens? I mean, if it's 0. If voltage here is 0, I mean, let's again assume battery is infinity. You get output is what? Minus 0.7, right? If the top is on. But if the top is on -7, you get a current going up, but bottom is off. Current has nowhere to go, so it's impossible. Now, if you assume bottom is on, which means this is going to be 0.7, then you have current flowing down, which is also not possible because the up is off, right? So when between 0.7 and minus 0.7, this circuit is going to be off, no output. Output will be 0. But above 0.7, the top is on. Below 0.7, the bottom is on. This is circuit. Yeah, go ahead. Oh, 101 is beta +1. Yeah. No, in this final solution, no, it assumes beta equal to 100.
It was given,
Yeah,
it was given actually 3 slides ago.
yes, it has given. So when I did the problem, I assumed beta is infinity. So we did all those, but then we switch back saying, okay, your beta is not 100, what happens? So this is the solution. Yeah. So usually it's given in a problem. It would say either beta infinity or beta is given number. Yeah, go ahead.
So the thing that's confusing me here
Yeah.
is what are we doing to get the current through this resistor? Why those numbers? What's going on here? Because we're adding a resistance divided plus beta plus 1.
You're talking about equation 1.
Yeah, equation 1.
Oh, you're talking about equation 1?
Yeah, how did we get there? How did we get that full equation?
Oh, okay. Yeah. The thing that when you want to calculate when you want to calculate current IB, it's gonna be this 5 volts minus like 5 volts minus 0.7. And then minus all the way here. So there's a this resistance over here. So because bottom is off, right? Yeah. So the current over here is IE. Right. So let me see. So let me see. IE. So which means IE equal to IE equal to alpha plus 1 times IB, right? So when you write this equation, so beta, well, we can write this loop equation from here all the way to here. So you will be in the 5 volts equal to IB times this 10K plus 0.7, then plus alpha plus 1 times IB, then times this 1K resistance. It's just for the, for easier to understand, I write the loop equation from 5 volts all the way down to ground.
Why is it alpha?
Why is what? Oh, beta. I'm sorry. Yeah, you're wrong. I was going to write alpha, then I write plus 1. Beta plus 1. Yeah, thank you.
So why is alpha in the top one? Okay.
Oh, yeah. Those 2 weeks.
Yeah. Very good. Okay, so here, and you can see why IB is going to be 5 minus 0.7 divided by 10 plus this 101 times 1. Right, so that is the equation for this one.
Okay.
So as you guys, I want to summarize also here. You guys ask, what time? So if VBB, let's say this VBB. If VBB is larger than minus 0.7 but less than 0.7, we're always going to be 0. When VB larger than 0.7, then Q1 is on. When VBB is less than minus 0.7 and Q2 is on. So this is a typical power amplifier. So if the input, so what happens, like if you have, say, an input
Is it BB?
with
Is it BB or EB?
VBB, VBB, yeah. So if VBB like comes like this, and at the output, what do you get? So you get like something like this. So in the middle, there's nothing, but the the positive half minus 0.7 is amplified, but the negative half is also minus 0.7 volts, and it gets amplified by Q2. So it's like okay. So yes, go ahead.
9 milliamps exiting the node into.
Yes, same current, yeah. Yeah, so the 3.9 goes to the resistor here, also is a same current out of the E node, yeah.
Where it says 3, it's 0.039 milliamps entering, but there's nowhere where that same amount is exiting.
Well, the current, the arrow that I pointed, the red IE, is that's where it comes from.
It's coming from the positive 5 volts, the remaining current is coming.
Also, yeah, the 5 volts, it says 3.9 milliamps. And also inside the Q1, the base coming 0.039, those two added together is this 3.9, but it should be a little bit larger than 3.9.
Surrounded? Is it just like?
Well,
rounded?
I assume, no, actually what's going on
Yeah,
is that the 3.9 is the definite value and the 3.9 is the from the top is the average value. Because we used a loop analysis to find,
Something like that, yeah.
yeah, the 3.9.
mhm.
It's just the product, it's like that because the averages and the ambiguity.
Well, yeah, we technically, to find the current coming in, we just subtract 0.39
Yeah,
milliamps, but with
this value is
with two sig figs, it just disappears.
this is approximate. So this one should be, this should be 3.9 minus 0.039, or it could be like yeah, so that one is the approximate value, right? So it's not exactly 3.9. To the base class collector current goes to the emitter. And emitter current, everything goes to the 1K resistance, right? Okay. Now this is an interesting problem because every time, like when we do this problem, or we start to make mistakes, say, oh yeah, both seem to be okay if I show one on is off and show as this one, the other is off. But actually, it doesn't happen that way.
Just have to look at the sign, make sure. Like,
Yeah, then you have to look at, oh, there's a current flowing. Okay, well, the current has to go somewhere, right? So that's where you identify the problem. Yeah. We also looking at this problem, and what we did was we didn't go through the details to the problem. And the book, this is from the book, so you guys can read the book. So what the book did is initially it assumed the beta is infinity, and it started to do the problem, and then it added back IB2 into this IC1. So to resolve the problem, and then it compare the errors between them was very small, and saying, okay, it really. So what it did is like 2 iterations. The first iteration is assume beta absolute infinity. We got everything, but then by the time we got the solution, so we now assume beta is 100. We find IB2, and then we add IB2 onto IC1, and then we resolve every node voltage and every current. So that gives you a first pass approximation, which apparently is not exactly the solution. But the book says, yeah, but if you look at the differences, it's very small. So one of the students asked me, okay, well, I don't want to do that. I want to get exact solution. Am I able to do it? Actually, you can do it. It's actually not that difficult. It's just tedious, I would say, just because all the manipulation needed to verify all this loop and nodal analysis. So what we are saying is, of course, this is very important. You guys know the first step is to convert this into Thevenin's equivalent circuit, right? So when we convert that into a Thevenin's equivalent circuit, we got this. We got
Parallel. Voltage.
Of course, we don't see this type of circuit very often in this class, but when you get to 414, you will see this very often with multiple transistors in a circuit. So the first step is to do a Thevenin's analysis. By doing Thevenin's analysis, we know that the 15 volts is going to be divided by the 5 and the 10. So we got 5 volts as the input over here. And here it's still 15, right? And resistance is the 2 in parallel. So we got 33.3K.
Or all the black arrows on top of 15 volts.
What is it?
Yeah, all the black arrows on top.
Yeah, all the transistors, those two are 15, but the right hand on the base is 5. That's from the Thevenin's circuit.
Oh.
Yeah. So if we want to do a really good, like a detailed, like exact solution, assuming beta is also not 0, we can write a couple loop equations. The first loop equation you can write will be something like here. Cannot change the color, for whatever reason. Let me see if we can do this. No. Right. So, like you can write this loop equation over here. You can write a loop equation like this over here, or you can write a loop equation of. Let's start right one by one. So let's define this as 2. So from 2, you can see that if we write that loop equation, it will be 5 volts equal to IB1 times that 3.3K plus 0.7, and then plus this IE1 to 3K. So it's going to be 3K times IE1. And we know that IE1 is going to be alpha times IB1, right? So from here, you can easily find IB1, IE1, and also finally, you can find IC is equal to beta times IB1. So this the first step on the first stage is fairly easy, right?
Do we know what our beta was for this?
Yeah, beta is assumed to be 100. Yeah. No, beta has to be given, otherwise you can't solve the problem. So then by this point, so what happened is here, so IC1 is going to be IB2 plus, we call it I1. So IC1 is actually IB2 plus I1. And I1 is equal to what? I1 is equal to VCC minus VC1 divided by the 5K resistance. So VCC. And then what we find is RE2 here. We can write the other loop equation is from RE2. So that's going to be, let's call it 3. So step 3 will be RE2, this is 15 volts, equal to IE2 times RE2 plus 0.7, then plus VC1. So in this equation, we have two variables, so IE2 and VC1. But we know that IE2 equal to alpha times IB2. So from here, you can plug in this one to here, and also this one to here, right? So of course, we know that IC1 is already solved. So you plug in, so I'm not going to actually do the actual problem because it might take too much mass. But as you guys can see, so we have, so if we replace IE2 with IB2, so this variable is gone. We have IB2 as one variable. VC1 is one variable, right? So yeah, basically what I'm saying, we have two variables, we have two equations. We should be able to solve for it. It's just, again, just some mathematics we have to go through. And finally, once you do that, you can find an IC2 as well. So this is typical, like a BJT problem, where you have this multiple two-stage, this is two-stage, and we might have three-stage, four-stage amplifiers, and each stage would have some sort of coupling because IB is not 0. Now, initially, you can always assume B is better than infinity. We do the DC analysis and so on. So it wouldn't be too wrong. But often they want you to go back, saying, okay, let's now assume beta is not 0 to see what is the exact solution is going to be. So it's like a two-step. The first step is approximate. If the first step approximate already say, yeah, this like transistor operating too close to the saturation or too close to the cutoff, we say, oh no, it's not a good design. Let's revise the design. So that's why approximation is important, because it gives you like a glance. It gives you like a first look at what's, what it actually, look like. But then once you want this exact solution, you'll go back to the calculation. But of course, unfortunately, the Hanner waving calculation is only done by students like you guys. Now, because why? Because you want to understand the principle behind it. Once you got familiar with it, nobody does the Hanner calculation anymore. Everybody goes to a simulation, to SPICE, and that's your second project. You go to SPICE, so I can put all the parameters. Okay, this is the solution, which is even better because it uses the SPICE model, not the linear model that we're using. So it actually gives you much better, even more accurate solution based on the physics, right? So.
Because we're assuming they're acting like diodes with 0.7.
Right, that's our linear model. That's not the physics model. So even though we say it's exact accurate solution, but it's actually not based on the physics model. The physics model will give you a slightly different solution as well.
And we're also assuming, and there's another level of assumption we're making here, because we're assuming the diode equivalency when we are actually have that resistor in parallel with the current source equivalent circuit.
Yeah, I know. Yeah, no, that is, we're not using that here, right? Yeah. So basically, electronics is like this. You see, we have purely like approximation models, like linear models, 0.7 drop and so on. But then we have physics models, and then often like you go to the other VLSI and other like logic design, logic gates design and so on. It's even like further simplified. They don't consider the voltage drop anymore. So it's a 5, okay, it's on, it's 0. When it's off, it's 5. Actually, it's not, right? Because we know there's 0.2 volts drop across the transistor. So it's actually will be 4.8 instead of 5, right? But anyway, so for us to understand the basic principle is important, because later on, even if you do simulation, we'll say, oh, why is this happening, right? And if you don't know the principle behind it, you'll be troubled because you don't know where to go, how to revise design, how to look at the solution, if it makes sense or not, things like that, okay? So let's go ahead with just a few more things in this chapter will be done. So the one is we're looking at the exactly like let me actually go back once a blank page. So what we're doing in the future is we're going to do amplifier. That's the importance of this class. So when you do amplifier, we have an input and then we have output. So basically, if we use a MOSFET or we use a BJT, it doesn't matter. And we all, most of the time we use N-type as example, but again, it doesn't matter. It's P or N-type. Actually, we combine both in many applications. So when we say have a BJT, we use amplifier. What would you? So what we wanted to get out of this is actually some sort of either voltage or current, because that's what you want. So I give you a typical example, like a very simplified example of, and actually this can go to, let me do this. So now we're going to link this together with this circuit. So you see, I have a two-stage. So the first stage is a small signal amplifier. So I will explain a little bit further. But the second stage is a power amplifier. So what I'm doing here is from the first stage, I amplify like a very small signal to be a certain value so that it's usable. But still, it's a signal. It's not, does not have power, it cannot drive anything. But on the second stage, I will be able to drive, let's say, a speaker or a relay or something with much more current available. So how do you achieve that? Well, what we're doing is we're going to do let me do color. Let's call it what do we call this? Let's call it VB1.
Is that one the small signal?
Yeah, no, this voltage source is a
Chain.
yeah.
Chain.
Okay, well let's call it VI. Oops. That's called input. So typically you will have one is the capital VI, and then the other one is a large VI. We might need some sort of resistance here, just make sure that we don't mess up the operation. Yeah, we don't, okay, so this is. And so first of all, if we want to be able to operate this as an amplifier for the first stage, so Q1 needs to be in active mode. Okay, so suppose VI is very small, like in the millivolts. So it doesn't impact very much how the Q1 operates because it's in millivolts. So in order to have Q1 in the active mode, how much VI, the capital VI, do we need? Can you set it to 0?
Which VI?
The capital VI. Can it be 0? 0.7. So why not 0?
Because we need to at least have enough voltage to overcome the thing that makes it slightly more complicated is that we have the resistor between
Yeah, well,
it
you know,
and Q1.
right. But the base current, think about it, is very small. And when we do the initial analysis, we can assume it's even 0.
So if we're assuming it's 0, it's we need 0.7 because we're everywhere where the leg is an arrow, we're assuming there's a diode.
Yeah. So you need 0.7 to bias the base to emitter so that it can be forward biased, it can be on. So 0.7 is the minimum voltage. Because there's a resistor over there, you can be more than 0.7. That's why I added resistance. If there's no resistance, if you say 5 volts, you'll be in trouble because you can't have a base to emit at 5 volts. But since we have a resistor, you can have above 0.7, that's fine, because that resistor is going to limit how much current you can flow into the base. Right? So I1 has to be larger than 0.7 to be able to use this as an amplifier.
For that first step. Yeah.
Well, that's the first step. So and then VI is typically against small signal in the millivolts. Typically it's in the single digits, like 5 millivolts, 10 millivolts, whatever the number is going to be. So so in that case, you think about it. When we do this multiple voltage source circuit, especially when they're in series, one effective method is to use a superposition.
Yeah.
Right? You superposition. 2 voltage source. So for one current, because it's a linear circuit. So with one voltage get the output, and then so another one gets voltage, you add this two. That's your output. So in this case, in particular, true because that little VI is so small. The VI is capital is 0.7, and little VI is 5 millivolts. So 5 over 0.7, that's kind of less than 100%, less than 1%, right? So even we neglect that lowercase vi, you won't be too wrong for the circuit analysis when you do DC. Right? Okay, so lowercase vi is 5 millivolts.
5 millivolts.
Yeah.
Then
Yeah.
There's no. It's not in the active mode. We're in the saturation mode.
No, why? We don't know yet.
Saturation or
We don't know. Yeah, we know that it's going to be conducting. We don't. So in order to be in active mode, of course, we need to have another variable is that VCE1. So VCE1 has to be or larger or equal to 0.3 volts. That's another variable.
So then we need the RVs. The current at the node. So basically our VCE is just our current at our voltage at C.
Yeah.
Because
Right.
we know that VE equals 0.
Yeah.
Because we've defined it as ground.
Right. Yeah. Correct. You're right. But of course, at this point, you'll probably know that. Well, the trouble is that if we see is actually 0.3, the second stage even don't work, right? Because remember, between minus 0.7 and 0.7, the second stage
Yeah,
output is 0.
Because if 0.3 the second stage, everything would be at 0.3, and we're in between the two.
Yeah, it doesn't really work.
Because we're assuming infinite,
Yeah.
infinite B.
Yeah.
Infinite beta.
So here we call this one VI. We call biasing like voltage. So that VI, that capital VI, at a certain voltage to make the circuit into an active mode is a voltage we call biasing. If we remove that capital VI, the whole circuit is in the cutoff mode. It doesn't work. Regardless of how much lowercase vi you apply, it's not going to work Well, unless you go to like really beyond 0.7, but we're talking about small signal in the millivolts. So it doesn't work. So that's the term called biasing. So it's important we have to bias the circuit so that it works in the active region, or your MOSFET it's in the saturation region. That little Vi is called a small signal.
So we're trying to amplify little vi.
Yeah, we try to amplify little Vi, right?
So we're making VI that's larger. We're adding VI to,
Adding little Vi to the big Vi. Yeah, that's true. So
is vi a the little one, is that a sinusoidal?
it doesn't have to be sinusoidal, but it's always an AC signal.
But it's like so this is like a DC coupling situation where we increase it to kind of offset it, and then
Yeah.
later we would take it off.
They could take off the DC. Yeah, you see the yeah, exactly. So okay, so that's what we have, and then of course, the step to go through this will be to analyze the circuit, find. Okay, so basically the two steps will be step one is to do the DC analysis. So step one, you do DC analysis. This is sometimes also called DC biasing calculations. You find all the DC voltages and DC currents at each node and each branch. And then the second step will be doing the small signal. Now, of course, we're not going to do small signal yet today because we're going to start that next week. But what I want to illustrate is, let's say you on step one, you already find we see here, let's call it VO1. So VO1 equal to VC1, right? So that's our output. So that's stage one output. So here we have two stages, the first stage and second stage, okay? So VO1 is the output. Let's suppose you get VO1 already, a voltage, like because capital Vi is given and everything is given, so you got VO1 certain voltage. It's going to be something larger than 0.7, larger than 0.3, maybe it's even 5 volts, okay? So now you add a little Vi. Let me do it in this corner. Step two. So I'm going to draw a better picture here. So let's say this is your capital Vi, and this is 10. And you find your VO1, and this is 10. See, what I want you to say, okay, so for any given Vi, you will have a given VO1, that's fixed. Now, of course, you change Vi, the VO1 will change. But for all electronic circuits, we don't usually change the DC biasing. Once the DC biasing is given, we fix it. Well, what we change is little Vi. So we're not going to add a little Vi. So if you add a little Vi, let's say it's a sinusoidal signal here, right? So imagine that you add this little Vi on top of that capital Vi. What's going to happen at VO1? So initially, without little Vi, it's a DC voltage. Now you have a little Vi added. So imagine that it's going to have something. You're going to see something, right? So you might say, okay, what exactly? Well, you see, what happens is this. Like for any given circuit, I'm just having one voltage. What I can do is, for any given voltage, let's say initially 0.7, you got a certain VO1. So what is Vi plus Vi. So I'm gonna just having this little Vi and a capital Vi, they plus together. So if 0.7, you got a certain VO. And I'm gonna have Vi plus Vi is going to be 0.705. I'm gonna get another VO. I mean, if my Vi plus Vi equal to 0.695, I'm gonna get another VO, just different values. So VO 1, 2, 3. I'm gonna get like for every time. So what you can do is you will go do DC analysis. Just I'm not doing AC yet. I'm just going to do DC analysis. So every time I change Vi a little bit, the lowercase Vi, I just added on that capital Vi. So let's say initially it's 0.7. Now I have 0.705. Right? So I do the DC analysis. I do everything. Then I got like another output, and I got another output. So if you plot that like different points, and you would get something like this. And if you connect all these dots, you'll get something like that. Okay?
So is it bigger or smaller than our initial input? I mean, BI or.
Or typically it's much bigger, of course, we want to amplify. Right. But what I mean is that whatever that value is going to be, you're going to see some sort of changes in VO. So every point of Vi that change, it brings that change at the output. So what exact amount of change based on now you calculate the DC at every single step. But when you do that, you get some sort of numeric solutions, but that doesn't tell you what exactly the relations between these two numbers. So that's what we're going to do in chapter 7. Okay, let's dive into this, see what exactly happening. For any given number, how do we find the output as a relation of input, right? So I want to just for this, I'm going to just give you some clues, so we're going to get a good start next time to do. So, but there's one more thing. You see here, we have this input voltage has a ground over here, and also the emitter is also grounded. So the input voltage, especially the lowercase Vi and this emitter, they both are connected to the same ground. So we call this a common emitter amplifier. Of course, we're going to see this again many times. Also, why we call this emitter, a common emitter. Then we have common collector and common base. So by the name, you already probably know, if we say common emitter, which means emitter is grounded, because input signal is always grounded. Right? But of course, except for differential amplifiers that we don't study in this class. So input voltage is always grounded. So if the emitter is grounded, it's a common emitter. If collector is grounded, it's common collector. If base is grounded, we call it common base. Yeah.
So if there was a resistor on the emitter side, it would not become an emitter.
Well, it depends where you get the output. So we have a term called common emitter with a resistance at the emitter.
Okay. Engineers always making stuff up.
Yeah. It's a common emitter amplifier with a resistor at the emitter. So that's yeah. It's a nice item that you bring up. Okay. So so given that, we're going to look at this as called common base. Why is it common base? Well, basically, if you look at it, what they're doing, they're going to take output over here. When you take output here, basically, this IE at the bottom. So this IE is kind of your output right over here. So this, you take your output over here. And the base is grounded. And so this is going to be what we call, they call it common base. So when you have a common base, you measure the output over here. Basically, it's equivalent to measure the output of IE over here. And so where you see here is they're measuring IC with a relation to the input of VCB. So this is VCB. And you are measuring IC. And as you can see here, if VEB is 0, or if VEB is minus 0.4, this goes to, if VEB, VCB, okay. So VCB is here. So for VC to VB, remember, probably write down. So for this transistor to be in this active mode, we need a VBE to be 0.7, and we need VCE to be larger than 0.3. So if you summarize here, it says VBE has to be 0.7. Let's say just 0.7. And VCE has to be larger than 0.3. So therefore, VCB equal to VC minus VB. In this case, it has to be larger than 0.4 volts in order to be active. Had to be in active mode.
What does the strike through arrow mean again?
The error may change,
Yeah,
Like we
variable.
it's variable.
It's variable. Yeah.
Thank you.
So if you vary VCB, or if you vary VE, in this case, we have two variables to vary. So we vary VCB, or we vary, like we given IE, find IC as a function of VCB. So this is basically what it does. So for any given IE, I want to find what the IC is a function of VCB. As you can see, as VCB increase, that IC actually is almost constant, right? Because that's a characteristics of this BJT. And then if we change VE, of course, if you change another VE, again, you find VCB. So eventually, what we know is, in fact, if it's in active mode, we know IE is equal to alpha times IC, right? So all IC equal to IE over IC, IE over alpha, right? So it's really very simple to look at the relations between IC. You can say, if you think beta is infinity now, alpha is 1, so therefore IC is actually equal to IE. So what it means that if IE is given, you get 1 IE here in this region. But if VCB is too small, you actually get into this saturation region. Now it's no longer true. So IC is no longer same as IE. The difference becomes bigger and bigger. So this is what this table tells you. Okay. Now we have two more things to talk about. And this one measures a common emitter. So the previous one is common collector, now it's common emitter. So what we're measuring is, we measure the relation of IC as a function of VCE. So what it says is that given IB, find IC as a function of VCE. Now we know this very well because we know that if VCE is too small, it's in saturation. So it's in this region, saturation. In the middle region is active. And if it's too much, it goes actually to no longer, so there's three regions, active region, saturation region, there's going to be what we call also a breakdown region. So it's too much voltage, it's not working anymore, right? So finally, this also, transistor also has quite a bit of relationship with the temperature. So remember we tell you this IC equal to IS over times e to the VB over VT. Guys, remember this equation for diodes and BJT? So for this one, we have VT, we assume to be 25 millivolts. Actually, this is corresponding to 25 degrees C. Now, if T change, VT actually change as well. So the more temperature, the more active the electrons can flow, I think. So equivalently, the VT will go down because you can think about it, right? So well, that cannot be true. Like in a conductor, when temperature goes up, resistance goes up, so current goes less. So in this case, what we say is they give you a relation, typical relation. So when T is increasing, that beta increases, and also IC. That's a I mean, this relation shows the relation between beta and IC. So you can see beta is actually changing as a function of IC, but also a function of temperature. So beta goes much bigger when temperature increases. So when temperature increases, beta increases. So, so in summary, we have two kinds of BJTs. So we have NPN and PNP. So in a NPN, VBE is what we measure, and VCE is what we measure. In a PNP is VEB and VEC. And the current flowing IC is equal to IS times e to the power of VBE over VT. And VT assume 25 millivolts. So this are quite the basics of these two BJTs. And a BJT can operate either in cutoff or saturation or active mode. And the condition to be in cutoff is VB less than 0.7. If VB is larger than 0.7, it can be either in saturation or it can be active. In order to be inactive, VC has to be larger than 0.3 volts. Okay. So that's what we give you a condition over here. So 0.3 volts is edge of saturation, 0.2 is in saturation, VB is 0.7. And the relations between, in the active mode, the relations between current is this couple equations you guys have to, should be memorized by now. It's IB is IC over beta, and IE is IC plus IB, and IC is alpha times IE, and alpha, of course, is beta over beta plus 1. And also, finally, we did talk about early resistance. The early resistance means that IC is not strictly constant. It's actually a little bit increase as we see increases, right? So remember this equation, the final drawing I want to draw here is that this is the typical current and voltage curves. So IC is a function of VCE, but also a function of VBE, and when VB increases. Now, of course, once we get the 0.7 thing, we now went back. See, we only choose that one curve that is equivalent to 0.7 volts. You know, in real world, the VB changes, actually this curve actually changes. But regardless how it changes, if you extend this slope all the way down to this quadrant, you will see VA. It's going to be your early voltage. And early voltage divided by IC, that gives you the early resistance. And that's where our equivalent circuit had that resistance in place. Okay. So I think that's all we cover in chapter 6. And any questions?
So between 0.3 and 0.2, what does that look like for BCE?
It just saturates, but it has not fully saturated yet. It's like when you eat, you think you're full, but you can still eat a little bit.
But in saturation,
The
that's
saturation, that's it.
right, but that's like the active, not saturation is the curve mode, right? Or
Saturation is the curve down at the corner over here. Over here.
so it's kind of, so if on a problem, say BCE was less than 0.3, could I say that it was in saturation?
Yeah, you said it's saturation. Yeah. But if we say it's in saturation, you say we see 0.2.
Okay, so if I'm solving
Yeah.
a problem,
If you got VC less than 0.3, yeah, you can say it's in saturation. Yeah.
all right.
Yeah. Okay. Well, if no questions, we're gonna look forward to the second midterm on Thursday. Good luck. But I have my office hours today.
Possible to release the problems early, like you did last time, in the last exam, just so that we can kind of double check.
I think it's already released.
The solutions are already, is this the one due tomorrow?
Yeah, it's already possible.
Oh, okay.
It's already possible. Yeah.
Just
Yeah.
to confirm, midterms on Thursday.
Yeah. Yeah.
Okay. Just make sure I didn't see it on the calendar, but I saw it on the syllabus.
Yeah. Yeah.
Last things to review for the midterm.
Well, good.